You are currently the only person in this conference.
So the goal of the exercise session of today is the design of a buck converter we all know the buck topology. Switch the diode, the inductor, and the output capacitor with the, yeah, we have of course the load IO and the output voltage VO with the following specifications, with the following specs. We have an input voltage which ranges from 8 up to 24 volts. In a switching mode voltage regulator, the input voltage is not constant, is expected to vary in a range, and the regulator should be designed to get a constant output voltage, okay? And in this case, we want an output voltage which is 5 volts. And on this output voltage, we accept a ripple, a peak-to-peak ripple of less than 50 millivolts. That is 1%. Okay. The maximum current that can be drawn from the load, IO maximum, is 2 amps. Okay, so these are the specs of our buck converter, and we want to operate it in CCM. Typically, buck converters are operated in CCM to reduce the stress in the components, and also considering that this topology, continuous conduction mode operation, is okay, does not give any kind of problem in the control, unlike other DC-DC converters, okay? Let me say that these specifications are the typical specifications for vehicle applications. These input voltage range is the typical minimum and maximum voltage that you can expect to have in a vehicle, at cranking, and possibly at when you have or possible overvoltage. These are the typical specifications for a vehicle. Okay, now let's start the design. Of course, if you have any comment, any question, please write in the chat so that I can immediately answer. Okay. So the first requirement is that the converter should be operated in continuous conduction mode. We know that the choice of design the converter, first of all, means to choose the components, not just the value of the components, but also the part number, so that the components can be bought and can be the circuit can be actually mounted on a printed circuit board, on a prototype. Okay, so this is our goal, to choose the components, the capacitor, the diode, the switch, the inductor, the capacitors for this converter. Now let's start with the requirement on continuous conduction mode operation. In order to operate the converter in continuous conduction mode, we know that operation in continuous conduction mode is basically related to the fact that the inductor current which flows through this inductor should never go to zero in a switching period. Okay, it means that its minimum value should be should be more than zero always. Okay, considering that the mean value of this current is basically the output current, these conditions should be most critical to be met when the load current is minimum, not when the load current is maximum. Okay, so if we write the condition for continuous conduction mode operation, we get that the inductance should be larger than R maximum, where R here is V out over IO, VO over IO, times 1, or better, let's start. The general condition for continuous conduction mode operation is that R times 1 minus the duty cycle divided 2 times the switching frequency should be, the inductance should be larger than R times 1 minus the duty cycle over 2 times the switching frequency. Since the inductance should be larger than something, this condition is most difficult to be met when this expression here is maximum. To maximize this expression, we choose the maximum value of the output load. This is actually the load. And to maximize 1 minus D, we have to choose the minimum duty cycle. Okay, now let's evaluate these quantities with reference to our specification. R maximum, R, as we have said, is V output voltage over output current, and this is maximum, of course, when the output current is minimum, for the reason that we have just discussed before. Okay, So when actually in our specifications we do not have a minimum output current. So how to choose the minimum output current? Well, there is a trade-off. If we want continuous conduction mode operation down to a very, very low current, actually down to current tending to zero, we get that the inductance becomes very, very large, and so it becomes more expensive. It becomes possibly bulky. It takes a lot of space. Its weight is not negligible. So in practice, let's say that for IO minimum, a typical assumption is to take 10% of IO maximum. Okay, this is something reasonable. We have 2 amps of maximum current. IO minimum will be 0.2 amps. Okay, if we put in this expression the output voltage is 5 volts, IO minimum is 0.2 amps, what we get is that R maximum is 25 ohm. This is the first element we need in this expression. What about D mean? What about D mean? Well, we have a buck converter. We want to operate in continuous conduction mode. In continuous conduction mode, we know that V out VO is D times the input voltage. So the duty cycle is VO over V in. First of all, let me make a remark. We can observe from the specifications that these specifications can be met using a buck converter, since we have always VO less than V in. Of course, if this condition is not verified, we could not use a buck converter, because we know the buck converter can only reduce the input voltage. It cannot increase it. Now let's discuss what is the minimum duty cycle. Since VO is fixed, in order to get the minimum duty cycle, we should consider the maximum value of the input voltage. Let me say that in this analysis, I have neglected the voltage drop across the switch and across the diode. Actually, if we should consider the voltage drop, why I have neglected it? Because if I consider the voltage drop across the on switch and the on voltage of the diode, VD, what I should get, instead of having, we impose the steady state condition on the inductor, instead of having V in times T on is equal to V in minus V out. is equal to V out times 1 T minus T on, or if we divide by the period, we get this is the duty cycle, and this is 1 minus the duty cycle. This is under with ideal components. If we would consider the voltage drop across the switch when the switch is on, so during the on phase of the switch, when the switch is on, we will have that the voltage across the inductor is not V in minus V out, but it is V in minus V switch minus V out. We would have V in minus V switch minus V out. And in the off phase, when the diode is on, we would have that the voltage across the inductor here is L, is not just V out, but it would be V out plus VT, the voltage across the diode. If we take into account of this non-ideal behavior of the components, by the way, we can, this times D, we can get that V in times D minus V switch times D minus VO times D is equal to VO minus VO times D plus V switch times 1 minus D. These and these cancel, and we get, if we get the expression of VO, we get that VO is no longer V in times D, but it is V in times D minus V switch times D time minus, this is not V switch, this is V diode, minus V diode times 1 minus D. Or in other words, we can say that this is V in times D times 1 minus V switch over V in minus VD over V in times 1 minus D over D. Okay? But so we can observe that due to the component, to the voltage drop across the switch and across the diode, we have that the output voltage is the ideal one, V in times D, times this factor that is less than 1. In other words, if we want to keep the same output voltage, we have to use a duty cycle that is larger. So if we need to know the maximum duty cycle, we have to take into account of the losses. But if we need to know here the minimum duty cycle, it is a conservative assumption to consider the ideal case, to neglect the losses. If we include the losses, we will have that this duty cycle will be larger than this. Okay, this is the reason why I have neglected the losses. the diode and the voltage drop across the switch and across the diode, across the on switch and across the on diode. So under this assumption, is that clear? Is that clear why I have neglected the losses, the voltage drop across the switch and across the diode? Okay. Now let's put the numerical values here. So this is 5 volts. This is 24, if I'm not wrong. V maximum is 24 volts. So in the end, we get that this minimum duty cycle is 0.208. Okay. Now the last thing that we have to that we need to know in this expression is the switching frequency. Well, actually, the switching frequency is choice of the designer. The choice of the switching frequency is dictated by several design considerations. First of all, let's say that for an output power less than 1 kilowatt, the switching frequency could be in the range from 100 kilohertz up to 1 megahertz. Whereas if we target a power that is larger than 1 kilowatt, the frequency should be lower. Generally speaking, the higher the power, the lower the frequency. This is related to the devices that should be used, to the losses of the devices to be used, and also to other considerations. In this range, for instance, if we choose a higher switching frequency, and this is clear from this expression for operation in continuous conduction mode, the higher the frequency, the smaller is the inductance. It means that the converter can be smaller, can be also less expensive, because inductors are expensive components. Okay, so this is of course something positive. By contrast, we have that increasing frequency may require devices which are suitable to operate at very high frequency. In particular, if we move towards the megahertz range, it could be challenging. We may have more switching losses. Typically, while the frequency is increased, switching losses become more and more relevant, whereas while reducing the inductor and while reducing also the ripple, possibly conduction losses can be reduced. So there is a trade-off. If you increase the switching frequency, you may have more problems in terms of interference. Okay, this really depends on the application, but a general rule of thumb is that when the power is rather low, we can move towards high frequency. When the power is rather high, we have to go to lower frequency. One more thing, if we wanted to use transformers in our DC-DC converters, it is advisable to use a low frequency. In this case, we do not have any transformer. We have rather low power. The power of our converter is maximum power VO times IO max is 10 watt. That is not that much. In theory, we can choose a rather high frequency. Either way, also in order to avoid specific challenges, a good compromise that we will follow in these exercises to choose a switching frequency of 200 kilohertz. By the way, the choice of the switching frequency is not a trivial task. It should be done considering many requirements. Okay. One more requirement in the choice of the switching frequency, for instance, the range. If the switching frequency is below 20 kilohertz, the converter can generate audio noise, so it can become noisy. So it should be avoided if you have, for instance, something that could some applications in which this noise could be audible by the user. Okay. In this specific example, we will choose a switching frequency of 200 kilohertz. If we put all together in our expression here, what we get? We get that the inductance should be larger than 25 ohm times 1 minus 0.208 over 2 times 200 kilohertz. If we do this calculation, we get that L should be larger than 49.5 microhenry. Okay. Well, this is not. This is the requirement we got for CCM. L should be larger than 49.5 microhenry. What value of L do we choose in practice? For instance, first of all, we have to take into account of some tolerances in the component values. We have to take into account also that when inductors operate close to saturation or approach the saturation of the magnetic material, the inductance value is decreased. So it can be advisable to increase the 'inductance value of 10–20% factor. Okay. Not too much, because as we have already said, if we choose larger inductors, we increase cost, we increase the size of the converter, so this should be avoided. Let's say that a 10–20% margin can be reasonable. Okay. One more thing. Very often we do not have to design the inductor, but we have to choose and buy an inductor from a catalog, maybe or simply in a store, in an electronic components store. The inductors which can be found in commerce typically have an inductance value which follows the E12 series. You know what is the E12 series? Basically, you should know it for resistors, is the series of resistors with plus 20%, 10% tolerance, is the series of values 10, 12, 15, 18, 22, 27, 36, 47, 33, 39, 47, 56, 63, and 82. This is something that one should, an electric and electronic engineer should know this series of values, because these are the standardized values. So you cannot find, of course, an inductance of 50 microhenry or 60 microhenry. You can choose an inductance with one values which are taken from this series. So what is the next value that in this series that provides an inductance that is larger than 49.5 microhenry, that meets the specification and with this safety margin and is in this series? What value should we choose? Do you give me some feedback? You are engineering students, so 56 is the good candidate. Let me say that also 68 could be, sorry, this is 68, not 63. Also 68 could be reasonable to take a larger safety margin, but of course, higher values, 82 or 100 microhenry, could be too large. So let's say that 56 microhenry could be a good choice. Are we over with the inductor? Not yet, because in order to choose an inductor, we should not just give the value of the inductance, but we should also provide other specification to properly choose the inductor. In particular, we need to know the RMS current which flows through the inductor. We need an inductor that is suitable to sustain the RMS current which is expected to flow in our buck converter. And we also have a specification on the maximum current value. The maximum current value is related to the saturation. If the current flowing through the inductance is too high, the magnetic material is saturated and the inductor does not work anymore as with the inductance value which is expected. So we have to go back to our to the waveform of our inductor current, and we need to calculate IL maximum and IL RMS. For what concerns the IL RMS, since in a buck converter in CCM normally the ripple is quite low, since the ripple is quite low, we can assume that the RMS value for this kind of waveform that basically has a dominant DC component and a relatively low ripple, we can safely estimate that IL RMS is equal to the maximum output current. So we can say as a requirement for our inductor, the IL RMS should be larger than 2 amps. Okay, this is true just for the buck converter. For other converters with different waveforms, this could be for the buck converter in CCM, because in discontinuous conduction mode, of course, the RMS component can be much larger than the DC component. But for the buck converter in CCM, this could be a reasonable assumption. In order to get the maximum value of the inductance, if we have, since we have this situation, we have that the mean value of the inductor current is the output current. The maximum value would be the output current plus 1/2 the ripple. Okay, this is can be observed graphically from the waveform of the inductor current. Okay, this is the mean value which corresponds to the load current, and if this is the ripple, the current ripple, IL maximum is IO plus 1/2 of the ripple. What about the ripple? We can calculate it, for instance, considering the discharge phase of the inductor. The slope here is equal to the output voltage. I choose the discharging slope because the discharge depends just on the output voltage, which is constant, while the input voltage varies in a range, so it's more convenient to consider this part. We have VO over L. This is the slope times this time is equal to 1 over the switching frequency. Let's call this T2 times 1 minus the duty cycle. This is 1 minus the duty cycle over the switching frequency. We want the maximum value in the worst case condition to design our inductor, so we want this maximized. We want this maximized means that we take the minimum value of the duty cycle. Minimum value of the duty cycle is what we have already calculated before. We have all the elements. VO is the specified output voltage, 5 volts. L is the value of the inductance that we have just designed. Here we have chosen the minimum duty cycle, so this is 1 minus 0.208. This is the minimum duty cycle that we have obtained before, and this is 200 kilohertz is the switching frequency. If we put all in the numbers and we calculate this expression, we get that the ripple is 0.35 amps. So the maximum current is 2 amps. Take the maximum load current plus 1/2 of 35 amps, so 0.35 amps divided by 2. That is about 18 amps. So this is 2.18 18 amps. So at the end, when we have to choose to look at our catalog, we should look for an inductor with 56 microhenry inductance that is suitable to sustain an RMS current of 2 amps and a maximum peak current of 2.18 amps. Now we can say that we are done with the inductor. Okay, is that clear how to choose the inductor? Now let's move to the diode. How to choose the diode? First of all, we have to consider the waveform of the diode current. We know the inductor current. We are in CCM. The diode current is equal to the inductor current when the diode is on, so in the second part of the period when the current is decreasing. And based on the waveform of this current, we can choose an appropriate diode. For instance, we require that the diode can sustain a peak current that is equal to the maximum current that we have found before. The peak current in the diode is the maximum current in the inductor, and is the 2.18 amps that we have calculated here. Okay, it's the same value based on this plot. It is quite clear. Yeah, of course, it's periodic. The average current in the diode, basically we have to calculate the time average of this waveform. To be precise, we should integrate and evaluate the area of this trapezoidal pulse and divide it by the period. Again, we are in a buck converter and we are in CCM. We can say that we consider this equal to A0. We do not have a very large error, and we can estimate the average current flowing through the diode as I0, assuming that this current is equal to I0, neglecting this. Sorry, seems there is problem with the board. Oh, sorry. Let me okay. We have recovered our yes, but we have not the last part. So let me gets again the waveform of the diode current. We have said that this is ID. We have said that I, the maximum, is equal to IL maximum, and based on what we have calculated before is 2.18 amps. And we have said that I, the averaged, can be estimated neglecting this ripple in the current as the output current times 1 minus the duty cycle. Of course, we need to choose the diode considering the maximum average current that it can sustain, which is maximum if the duty cycle is minimum, if this quantity is minimum, and when the output current is maximum. If we put the values, the output current is 2 amps, this is 1 minus 0.208, the minimum duty cycle, we get 1.58 amps. Okay. What is the last thing that we have to choose for the diode? We have to choose the maximum reverse voltage that it should be should sustain. We consider our buck converter. Okay, we know that when the diode is when the switch is on, the diode is off, and the voltage across the diode is minus V in. Okay, the maximum reverse voltage that can be sustained by the diode is minus the maximum value that can be taken by V in, so minus 24 volts in our example, in our exercise. V, the max in magnitude should be larger than 24 volts. Okay? There are no normalized values for diodes, but it makes sense to take some margins, so we can consider to choose a diode with is suitable to sustain an average current larger than 2 amps and maximum reverse voltage, let's say, of the order of 40 volts. Okay, even if this is quite larger than the maximum expected value of the input voltage. Okay, and let's say that this specification, this reverse voltage is large, but let me say it's not a very, very large value for a diode. So we can use a Schottky diode. Schottky diode, which makes it possible to have lower forward voltage, so lower losses and higher efficiency. This is compatible with the Schottky diode, and it could be advisable in this application to choose a Schottky diode. Okay, and that's all for the diode. Is it clear? Any comments on the choice of the diode? Basically, we need to know the peak current, the average current, and the reverse voltage, the maximum reverse voltage. And we have to choose the diode accordingly. Well, this is, I have told that there are no normalized values for diodes, but it is the value of a rather low voltage diode to take a safety margin. Let me say we should take at least 20% safety margin. We would get something like 30 volts. Okay, 30 volts is not a common value for a diode. Of course, you should choose a diode with a larger reverse voltage. This 40 volt value is not so large. Let me say that if we can use a Schottky diode, this is typically a good choice. I think there is it is important for the reverse voltage. It is probably more important than for the maximum current of the inductor, for instance, to take a safety margin, because we can have in a vehicle over voltages, transient over voltages, for instance. So I think this is reasonable. And let me also say that probably there is not such an advantage in terms of cost, in terms of performance degradation, in choosing a diode with a voltage of 40 volts. Okay, if we do not have any particular reason to be more to take the margins more tight, we can also consider larger margins. Now let's go ahead with the switch. In this frequency range, let me say that if we consider MOSFETs, BJTs, and IGBTs, for this frequency, 200 kilohertz, we should not consider BJTs, since we do not have very large reverse voltages to be blocked. We do not consider IGBTs. The best choice is for sure MOSFET. Okay, what should we specify about the MOSFET? Well, the two main parameters to be considered are the VDS maximum, the maximum reverse voltage which can be sustained, of course, and the RDS on, which is related to the losses, to the voltage drop across the switch, and to the losses, and to the end to the efficiency of the converter. What about the maximum voltage across the switch? We have the maximum voltage across our switch when, of course, the switch is open. And when the switch is open, the diode is on, and the voltage across the switch is Vin. Again, VDS maximum should be larger than Vin maximum. Vin maximum is 24 volts. Again, it could be advisable to choose a MOSFET with something larger voltage, for instance 40 volts. Okay, but what is interesting to consider is how to specify the on resistance of the voltage. The problem, the choice of the on resistance is related to the fact that the on voltage of the switch, of course, is the current which flows through the switch times RDS on. We can accept, we can consider the discussion that we have presented here. Actually, in the expression of the efficiency, you have something like that. You can see that what really matters is the ratio between the on voltage across the switch and the input voltage. Okay. So typically we specify that this ratio is from 1 to 5%. We want V switch over V in from 1% to 5%. It means in our case that since V in is 5 volts, we can accept, let's say, 0.1 volts of ripple. If we want 0.1 volts of switch voltage, we can get a specification on RDS on. We get that RDS on should be less than the maximum voltage drop on the switch that we can accept, this 1/5% of V in, over the maximum current which can flow through the switch. The maximum current which can flow through the switch is again the maximum current which can flow through the inductor, the quantity that we have evaluated before is 2.18 amps. From this, we can get 0.1 volts over 2.18 amps, and we get 46 milliohm. Okay. Now you have to pay attention when you choose the switch based on the RDS on specification. You have to pay attention because in data sheets, what you normally find, it is something that we have already discussed when talking about devices. You get that you get RDS on at ambient temperature of 25 degrees. But in practice, your converter, depending on the heat sink, how the converter is designed, but very typically, operating temperature can be in the range of 50 up to 100 degrees, which is larger than ambient temperature. We know that the on resistance of the MOS transistor increases with temperature, and compared to 25 degrees, the resistance that you can find at 100 degrees can be 2 times larger. So the reason why in datasheets they report these quantities, because it is smaller, it seems that the device is better for commercial reasons, let's say. But in practice, what is important for us in our design is the value of the resistance at the working temperature. As a consequence, if we take this 2x factor that can be reasonably conservative, if we want RDS on of what we got is 46 million at say 100 degrees, we know that it means RDS on equal to, let's say, 20 or smaller than 23 million at 25 degrees. When you get the specification, you look in the data sheets, you should divide by a factor 2 the RDS on requirement that you find based on your specifications. Okay, and basically you have to look in the catalog for an MOS transistor with VDS maximum larger than 24 volts and RDS on smaller than 23 milliohm. Another remark, but this is not covered in this design exercises, in the buck converter, the switch is in a high side configuration, so you should pay attention. You need a high side driving shim unless you use a PMOS device. Okay. Now let's conclude our design with 2 important elements that should be never neglected and should be also properly designed, that are the input and the output capacitors. What should we specify about the capacitor? First of all, before moving to the capacitor, is everything clear concerning how to choose the MOS transistor, the voltage and the RDS on? Is that clear? If it is clear, we can move to the capacitors. C in and C out. The most important parameter parameters that need to be specified are very interestingly are not the capacitance very often, but the RMS current, the maximum voltage, and the equivalent series resistance. But let's enter into the details of the design. First of all, I think that it is quite straightforward that the capacitors should be chosen so that to sustain, let me show again the schematic of the buck converter. This is C in, this is switch, this is the diode, and this is the inductor. This is the output capacitor, and this is the output current. First of all, the capacitors should sustain the voltage across them. The voltage across the input capacitor is the input voltage, so the maximum voltage across the capacitor would be the maximum input voltage, in our case 24 volts. Capacitors are normalized, the values of capacitor voltages are normalized according to the R5 series. So you have values like 10, 16, 25, 40, and 63. 5 values per decade. Since our specification is that the capacitor voltage should be larger than 24 volts, a reasonable choice, considering that 25 is very close to 24, to take some safety margin. A reasonable choice should be to choose a capacitor of 40 volt as a normalized value. Okay, 25 is also good, but is too close to the minimum. For what concerns C out, we have that VC max is equal to VO. In theory, VO should be constant. So VO is 5 volts. We take a normalized value. In this series, the first value above 5 would be 6.3, but it is quite close to 5, so probably a better choice would be 10 volt. Okay. So first parameter to be chosen is the maximum voltage. Second important parameter, we have to move Second important parameter is the RMS current. Why there is a concern about the RMS current? Because the current flowing in the capacitor, the AC component, may increase the temperature of the capacitor, and at the end this could also damage the capacitor. So if this value is not properly chosen, you can have very, very serious problems. So it is to be taken into great consideration. How to calculate the waveform of the RMS of the car, how to calculate the RMS current flowing through the capacitor? Well, first of all, since the current flowing through the capacitor is the inductor current minus the load current, basically we have that the load current is a DC current, while the inductor current is this is IO, this is IL, we get that the capacitor current IC is basically the AC component of the inductor current. So the current flowing through the capacitor is as a triangular waveform shape, and its RMS value is equal to the peak-to-peak ripple delta IL that we have calculated before, divided the square root of 12 to square root of 3 was 0.35 amps divided square root of 12. That gives about 100 milliamps. This is our specification for the output capacitor. If we look at the input capacitor, what is the waveform of the current flowing through the input capacitor? Basically, the input, the current flowing through the input capacitor is the current flowing through the switch minus the input current that is expected to be a DC current, since we put the capacitor to filter out all the fluctuations, and we consider this is the current in the switch. Okay, sorry, this is the current in the switch. Again, we can assume that neglecting the ripple, this is about IO. Under this assumption, and considering that the RMS value of this square wave is most critical when the duty cycle is 50%, we can conclude that under this condition and under this approximation, I C in RMS is maximum is equal to 1/2 IO maximum, 1 amp. Okay, and we can choose the RMS current 1 amp of the input capacitor accordingly. Now let's move to one more requirement that is particularly important for the output capacitor. Also for the input capacitor, basically the same considerations apply, but let's focus in particular on the output capacitor. We know that, as I have said before, the current flowing through the capacitor basically is the ripple component. Since we have this current flowing through the capacitor, the voltage across this capacitor is basically this current times the impedance of the capacitor. In practice, we have that real world capacitors, and in particular electrolytic capacitors, which are used very often for as a C-in and C-out in these applications, have an equivalent circuit which is like this, that includes, of course, the capacitance C, but includes also a parasitic series resistance, ESR, and a parasitic series inductance, ESL. If we look at the baud plot of the impedance, the magnitude of the impedance of this capacitor, we get that at low frequency it behaves as a capacitor. So we have an impedance that decreases with frequency with a slope of minus 20 dB per decade. Then this transfer function has a zero that basically depends on the technology adopted for the capacitor, the type of electrolytic capacitors, tantalum capacitors, aluminum capacitors. These, the technology of the capacitor dictates the value of this zero that can be in the order of kilohertz up to tens of kilohertz, okay? And at higher frequencies, you have that the inductive component is dominant and the impedance increases with a slope of 20 dB per decade. But for the frequencies of interest, hundreds of kilohertz, we are frequency of interest for power converters, for our buck converter, for instance, we are typically in this region. And this is the reason why we do not care too much to the capacitance of the capacitor, but we care more on the ESR. If we want to calculate the voltage across the capacitor when the ripple current of the converter is flowing through it, when this is the waveform of the current, as far as we have said we are in this region, we can say that for an electrolytic capacitor, let's say this is for an electrolytic capacitor, we say that the ripple across the capacitor voltage, that is in our converter, is also the ripple on the output voltage, since the capacitor is on the output the voltage across this capacitor is the output voltage, so the ripple across the capacitor is also the output voltage ripple, is equal to ESR times delta EL. If we want a ripple that is less than what we specified, 50 millivolt, let's say delta VO max, we get that ESR of the capacitor should be less than our target ripple, our maximum ripple divided the current ripple. If this is 50 millivolt from our specifications, this is delta IL is what we have calculated many times, is 0.35 amps, 0.35 amps. We get that ESR should be less than 0.143 ohms. Okay? So our specification for the capacitor is not on the capacitance, but is on the ESR. We can check directly on the data sheets for a capacitor with a sufficiently low ESR, but we can also consider the relation between the capacitance and the ESR, which is dictated for electrolytic capacitors by the frequency of this zero. This frequency of this zero turns out to be 1/2 pi ESR times the capacitance. From this expression, we can derive the capacitance. We can derive C is in terms of the ESR. We can derive that C is 1/2 pi ESR times the frequency of the zero. We know that this is a capacitor, an electrolytic capacitor, let's say of rather bad quality, with Fz 3 kilohertz. Of course, the higher the better, the zero frequency. It means that the capacitor works as a capacitor up to a higher frequency. If we use a capacitor with a zero at 3 kilohertz and we want this, we have this target ESR requirement, we get that the capacitance of the capacitor should be larger than 1/2 pi ESR times Fz. If we replace the numerical values, we get 1/2 pi times 0.143 ohm times 3 kilohertz. If we solve, we get this is 371 microfarad. Again, we can choose the capacitance follows the E12 series, the first one we discussed. Let me show you again. They follow the E12 series. So our specification, capacitance larger than 371 microfarad can be met by a capacitor of 390 or 470 microfarad. Normalized becomes 390 microfarad or even 470. Is that clear? If we choose, and in some cases it can be also possible, to use not to use electrolytic capacitors, but to use ceramic capacitors, the discussion on the ripple is quite different. If we look at the impedance of ceramic capacitor, the equivalent circuit is more or less the same, but ESR is almost negligible. And for the frequencies, they typically show an impedance with this shape. So basically, there is a resonance here. The frequency of the zero is actually, we do not have this zero. We have two complex poles. And in the frequencies of interest for switching mode power converters, we are still in the capacitive region for the converter. In the capacitive region, you have seen, you should have discussed this in class. The requirement on the ripple can be met basically by choosing a capacitor which is larger than the current ripple divided 8 times the switching frequency times the target voltage ripple, the voltage ripple that we can accept. I will not show you the derivation because I expect that you have seen these in class. And using the values that we have in this example, 0.35 amps, 8 times 200 kilohertz times 50 millivolt, you get that the target, the required capacitance is 4.4 microfarad. That can be approximated to 4.7 microfarad in the E12 series. Okay. The remarkable thing is that you can see that the value of the capacitance that we require in case we use a ceramic capacitor or an electrolytic capacitor is completely different. In one case, we need 470 microfarads. In this case, we need 100 smaller capacitor, 4.7 microfarad. The point is that we do not have any specification on the capacitance, but especially for the electrolytic capacitor, but rather for the ESR. Okay, I think that's all for today. Do you have any questions? Do you have any remarks? On the design of this buck converter. Now we have completed the choice of the capacitor. Let me say that the same considerations apply for the input capacitor if you have an input ripple requirement. For the rest, I think we have addressed all the steps of the design. Any questions? It is not to be chosen. It depends on the technology. You can say, I want to use a tantalum capacitor. You know that for tantalum capacitors, Fz is 20 kilohertz, okay? Actually, you have to decide capacitors which have a lower ESR and a higher S. For a given technology, it is always the same. For a given technology. If you choose a different technology, possibly more expensive, you may have higher Fz. But for a same technology, no matter the value of the capacitance, Fz is more or less the same. Okay? Any other questions? Okay, I think that's all for today, and see you in the lab for those of you who will be there in the afternoon. Okay? I remind you again, the next class with Professor Musolino is on Monday. Okay? So thank you again for your attention, and see you at the next in the lab for those who will be there, and the next exercise for the others. Bye.